Well, welcome to Science Unwrapped. I'm Charlie Torrey from the Department of Physics here. I'll be sort of your guide through the evening, and I also want to say welcome to our remote viewers that we have here. And before I forget, I should say there's going to be about a 45-minute or 50-minute presentation. Then there will be about 15 minutes for question and answer, and that includes you, remote viewers. You may submit questions, and they have to wait for a moderator, is that right, to enter the chat room before you can submit your question. So wait for that at the end of the talk, and you can be included in the discussion afterwards. So please try to participate in that. I should add, has everybody done this? Yes? You can do it. If not, you can do it while I'm talking. Okay. What I'm going to say is not so important, but anyway, I should say that the series that you're attending here, the lecture series, is sponsored by the College of Science. Okay, and we're very grateful to them for supporting this for decades now. And there's also a committee, of which I'm a member, who organized this thing and lasso people to get them to speak for us. And I want to thank the committee for all the work they do. Some of them have to actually clean up tonight, so thanks for that. And I want to thank also our fearless leader. The leader of the committee is a Professor Greg Podgorski, who, if you come here regularly, you usually see him in my spot. And that's because he had to be out of town, and I'm filling in. But he actually shoulders the lion's share of the load here. And so we couldn't do this thing without his effort. So I want to make sure we thank him. There's a lot of volunteers that are outside, the ambassadors and so forth, helping this thing go. I'd like to thank them. We have a number of after events this time that you can participate in after the talk out in the building. There's some activities, and I want to thank the members of the university community and actually sometimes the broader community for organizing that for us. That's a lot of fun. I should say that we are getting ready to start another series of Science Unwrapped next fall, in the fall semester in September. So we're working on that, and so stay tuned. That's on its way. That's all the business. Let me introduce our speaker and get down to the fun part. Our speaker is Professor Regan Zane from the Department of Electrical and Computer Engineering. I don't know where you grew up. I think it's Idaho.
I grew up in Idaho.
Aha, it's detective work. Google. Okay, so you grew up in Idaho.
You can tell from my accent. Is that right?
No, I can't, but it's hard to find. It was nowhere. Anyway, he told me, or I found about him, that he had a dream growing up, which was to be a pilot. Not just aircraft, but spacecraft also. Pilot and astronaut was one of his early dreams. Many of us who got into science and engineering started with that dream for sure. He went on to study engineering at the University of Colorado at Boulder. And there he got involved in some undergraduate research projects in a number of labs. And that was really what hooked him into the career, which he is now firmly embedded. After getting your undergraduate and PhD in 1999 at Colorado, you went on to work for General Electric, is that right, in New York. Came back as a professor at Colorado. That must have been kind of fun. We're a conquering hero coming back to the university. That's great. And then, was it 2012 we got you here?
Yeah.
2012, the university was very, very fortunate to get him to come and join us. He's one of our shining stars in the university, one of our most productive faculty members by far. I don't want to embarrass you, but there's nothing you can do about it, really. Not only is he one of the most productive professors we have anywhere in the university, I should just mention one thing, is he's the director of something you'll probably hear about, I assume, which is this National Science Foundation-sponsored center called Aspire. And those of you that are in academia know that getting the National Science Foundation to sponsor a center is a pretty big deal, and it's quite a seal of approval from the community. And so it just underscores his shining star status here. He's came here as a U-Star professor, I think, and has an endowed chair, and just is working gangbusters over there in the engineering school. I should say that he's not just a superstar geek at the university. He does lots of interesting things, has a family, travels the world, and finally met his dream of being a pilot He's a pilot and a flight instructor, am I right? Yeah. And so not only does he fly, but he teaches how to fly. And just one thing that's kind of cool that I read about him was that at one point he was lucky enough to be able to take off and land this aircraft from an aircraft carrier. So I can't even imagine how intense that must have been. And maybe after the talk, you can get him to tell you some of his adventures. But enough about that. Let's get down to the science and engineering. I should say we have an engineer speaking at Science Unwrapped. It happens. It happens sometimes. It's what I always say is that the future of science, or good science, is engineering, right? Because that's where it ends up. And so we'll see a little bit of that in action today. So anyway, Professor Zane, I'd just let you take over. Is that okay?
Thank you so much. All right, with all that embarrassment, now where do I go from here? An excellent memory, by the way. I'm quite impressed. All right, so I am an engineer, and I was invited in here, so I am going to convince you to be an engineer, but with one caveat, and I'll show that next. All right, so first, everybody done something like this. So we'll go ahead and we'll use the messaging to get in, particularly for those that are online, but also for those that are here. But also feel free to shout out your answers and raise your hand and interact with me. Feel free to stop me as we go. There's nothing here I have to get through, okay? So let's just enjoy this. Let's have an interactive discussion. And I know I'm going to enjoy it, and I do hope that you do as well. All right. First, I'm going to make sure that this thing actually works. So we're going to do a quick test with my first question, which you've already seen, those that have already logged in. Let's see what your answers were. Huh. Oh! Hey, this is going good. I like it. All right, so that was my first question. Who wants to be an engineer? And since I am in a science program here, I gave a slight option. Or would you like to work with an engineer, as part of your program in your career? Okay, this isn't too bad. I'm expecting to improve this through the rest of this talk, but actually it's a pretty high bar. I'm not sure how much further we can go with this. I like this audience. I'm pretty excited. We do have quite a range of an audience, so we'll see how well I can do at hitting this right at the right target of each of you. All right, so let's get going. We're going to see what it's all about being an engineer. We're going to put it specifically in the context of the program that I'm leading. My name is Regan Zane. I am the center director of a center called Aspire. It's an acronym full of words, but it's a program that's specifically dedicated to breaking down barriers to electric vehicles, and specifically to get each of you to buy an electric vehicle and live with it and own it and love it, okay? Our program is in particular looking at the charging infrastructure, the systems required to support these electric vehicles. That's really what we went to NSF and pitched, that's the next major barrier over the coming decade. So that is what we're addressing within Aspire. We are funded by the National Science Foundation as primary funding. We're also funded by a number of other government agencies, including Department of Energy, Department of Transportation, and others. And we're funded by the state of Utah and many of the other states of our partners. So there's a lot of excitement around this program. We've raised well over $65 million in the last few years for this program, and we're on a clear trajectory to have well over $100 million in this program within the next 5 years. So the question is, why is there so much interest in this? What's the excitement? What are we talking about? Does anybody care? Does anybody care to hear more? You do? It's about charging electric vehicles. All right, let's get into this. All right, so first let's just highlight kind of a vision of the future, and then let's get into a few details of the actual technology. So can we imagine this future where we have access, everyone has access to a whole suite of options for transportation, all modes of transit, everything from trains to buses to cars to the trucks that move your goods around. I mean, believe it or not, when you click buy on Amazon, it takes trucks and trains and all kinds of things to get it to you. It doesn't just appear at your door. Did you know that? There's a lot behind this. Can we imagine a world where all of these are available? Not only are they available and accessible to everyone, but they're all electric. They're coordinating their operations with the electric grid and with transportation systems. They're communicating with the roads and with the infrastructure. It's all balanced in a way so that it supports solar power and wind power and small amounts of energy storage on the grid. This makes our air cleaner. It makes our transportation cheaper. Did I hear a ooh yeah? Woo! All right. So that's the future we're talking about. So let's get into this today. This is going to take, again, a whole suite of technologies. And within the Aspire Center, we have over 9 universities involved, over 300 faculty and students involved. We are working on technologies across all aspects of engineering, particularly electrical and mechanical and civil, computer engineering. We have computer scientists. We also have a whole suite of others involved, from economists to other social scientists looking at the societal implications. This takes, I don't know, is an army a bad analogy? This takes the full community to sort out how to solve the challenge. All right, I'm introducing you to this first because now I'm going to dive into a few details of a few specific technologies, but I don't want us to get the impression that this one technology is a silver bullet or this one's the silver bullet. We're working on the whole suite, and I'll give you just a flavor of them. But here at Utah State University, we're particularly well known for one technology, and that is this idea of transferring power wirelessly. So let's just dive into what's cool about that. Then I'll convince you why it's necessary. Is that all right? All right. So let's get to it. First, I'm going to take you on a little tour. If you've been to our website, you've probably seen this video, a little tour around our track in an electric bus. But before I do that, let me just tell you, I love electric vehicles. Probably no surprise to you. Have you ever driven one? Just raise a hand. I don't have one of the questions. Yeah? You own one? Couple? Yeah? All right. I mean, the marvel of engineering. Yeah, look at this hand up here. See? Marvel of engineering. I mean, can you imagine? I mean, you're cruising down the road. I mean, my mind is just racing when I'm in an electric car. And I'm thinking, and I can just start envisioning. I mean, you're sitting on this giant pack of batteries. And you can just imagine this electrochemical reaction. I mean, it's expanding and contracting. And you've got electrons just coursing through the system. And we've got all these electronics inside of the system. And they've got these switches. And they're running at hundreds of thousands of times per second. They're switching hundreds of amps of current. And I mean, this is what you're thinking about when you drive an electric vehicle, right? And all this is happening, and it's going into this electric motor, and these electromechanical reactions happening, and it's creating torque, and it's spinning the wheels, and you're just cruising, silent, and it just keeps working. And anyway, it's very exciting. So I got to tell you, driving an electric vehicle is exhilarating. Not only because it's just fun, but you just imagine all the science behind it. Okay, but let me just tell you, that is here. Now let me take you around a tour of our track, where you've got that excitement running, and at the same time, that system is interacting with the road, charging the vehicle while you're moving over the road, while it's interacting and communicating with the rest of the world. It just takes you to a whole new level. So nothing better than this. All right, so by the end of this lecture, you are going to be dying to not only get an electric car, but drive it over an electric road. We all behind me with that? You behind me on that one? All right, so let's go on a quick little tour around the track. This is Brian, this is our lab manager. We're wirelessly charging the vehicle in motion. We've got these systems that are generating the electronics and current flowing through the road. It's interconnected to the rest of the system. We have these receiving coils. We have transmitting coils in the road. Now this is exciting, right? Let me just tell you a little bit. Let's just stop here, because this is the crux of the program. I thought we'd just dive right into the science, and then we'll get into the other details of why does somebody really care. But I mean, obviously you care because this is fun, right? This is exciting science. Okay, so what is this really? So we have a bus or any other vehicle. We have the road. Now in the road we have coils of wire, and I brought a couple of examples of those. Here's an example of wire. It's a specialized wire that's able to handle the types of currents that we put through the roadway, and you can come and take a look at it and handle it a little bit later. So in the road, we have a coil. It's in a shape, a rectangle, a circle, some shape like that. Okay, and then we use a few of what we call Maxwell's equations to make all of the magic happen. There's two in particular that we primarily leverage. Okay, one is called Ampere's law. It's pretty simple. Just means if you take current, pass it through the wire. Current's running through the wire. Okay, so as current runs through this wire, it generates a magnetic field. Okay, now you can't really see the magnetic field, but here you can. It's blue, it's shiny. Okay, so it generates this invisible magnetic field, which is pretty exciting. Now, if we make that field go up and down, we make it an alternating current, or an AC field, meaning it goes to a high peak and down to a low peak and back to a high peak. That means we generate an AC magnetic field. All right, that's the first key part, and that's coming from the roadway. Okay, so this is sitting down in the road, and it does that. Then on the vehicle, we have a similar receiving coil. And this is an example here of a receiving coil. This is one that is built by one of our partners, Witricity, and is similar to one that you would actually have on vehicles that could be available over this next year. Okay, so this little receiving pad is mounted on the vehicle, has cable, kind of like this. And what happens is it uses Faraday's law. Okay, so it recognizes that we have a magnetic field generated around this cable, because what's going through it?
Electricity.
Electricity is flowing through it. And as that current and electricity flows through it, generates the magnetic field. By Faraday's law, this AC magnetic field generates a voltage in the wire that's in the coil. Okay? It's as simple as that. And now when that voltage is generated on the coil from something like this, and it comes out a cable like this, that connects to a load, which is your battery or your motor on the car. That makes current flow, and that current charges your car and makes the car go. This is what Nikola Tesla was so fascinated by well over 100 years. He invented and developed AC machines, AC power, and he was looking at wireless power transfer and filed patents on wireless power transfer, the exact same thing that we're doing here. Now we're just at this perfect storm where finally the rest of the technologies, all of the rest of the circuitry and systems have caught up to Nikola Tesla 100 years later, and we're ready to really do this and do it at scale. Okay, so that's the basic concept. Can everybody see it? Can you envision it? I doubt it. So let me show you. All right, I do need a volunteer. You've been really good. All right. Can you tell everybody and show them, is it working? Is there a light? Is there a switch? No? Okay. So what we need to do is come up here and see if you can transfer power wirelessly from this transmitting coil to that receiving coil and get that light to turn on. Ooh. Now turn it so the audience can see it. Ah! Okay, so this is kind of fun. Now take it even a little further. Take it up over here, even rotate it. Now you'll notice when we get out, let's say out in this distance, the light goes out, right? In fact, I'll hold on to this. Well, you take that. Now we can even reshape the field. So we can take additional magnetic materials. And if you go ahead and bring this a little bit further away, you can see the light goes away. But let's just shape that field over here towards that light again. Or let's take the field back away. Or we could, shape the field like this, or down like that. Now do you visualize it? Is that fun? All right. Thank you. You're a great volunteer.
So that's a magnet?
There's no magnets directly in here, so there's no earth magnet. But what we do have is similar to an electromagnet, meaning we have a coil inside of this segment. We're passing current through that coil, so it's generated a magnetic field, essentially like an electromagnet. But now we have the receiving component on the other end. And instead of using this as a magnet to pull things together, like you would with an electromagnet, all it's doing is receiving that energy and now generating the light.
But the square, you said that had magnetic material in it?
Oh, good point. So in this case, that can be confusing between magnet and magnetic material, but this actually does have a magnetic material that allows it to help shape the magnetic field. And similar materials are used in this roadway. And so oftentimes we get questions, well, is it safe? Well, absolutely. How is it we couple so well to the vehicle? We have magnetic materials, kind of like this one, that shape that field just perfectly right up into the receiver, and it goes nowhere else. And there's no fields in the car, there's no fields on the side of the car. It would be more dangerous to hold your cell phone to the side of your head than to ride in a vehicle going over the segment. Question, yes?
What if the power goes out?
If the power really goes out and never comes back, we got serious problems. In these vehicles, the idea is we would have a relatively small battery, and if the power were to go out in a segment, you would just use that battery to get to the next segment, and then it would just keep you charging. If the power goes out in the whole city, you've got other problems too. But we try and get that power back. Interestingly, the power across the nation is over 99.7% reliable. So it's actually a pretty good source of energy for us. All right, so that's the basic idea, and that's one of the things I'm excited about. If we can keep it down to maybe 3 or 4 or 5 at a time, anyone who'd like to come up here and play with this, I actually have another one. This one also works. Maybe wants to try it out while I'm talking, no problem. Please, come play with it, see if it actually works. All right, so that's the basic idea. Next, we're going to continue our journey. Please, go ahead, I'll just keep talking. We'll continue around the track. All right, so as we're operating, the idea is this really needs to work for all vehicle classes. One shared infrastructure, multiple segments, receiving coils on different types of vehicles. They're all shared. That's the vision here of electric roads. Yes? Earthquakes, and even the construction of the material, the integrity of the pavement and the roadway. That's why we have a significant component of civil engineering involved in this entire program. If an earthquake were to come, and in fact we've run multiple tests, we have a lab here at USU called the SMASH lab. Structural, material, I forget what all it stands for, but that's where we actually smash up the concrete and verify how well is this going to operate, how robust is it. So we can actually survive a lot. We've been through a significant number of tests. We can have cracking concrete, we can have shifting in concrete, but if there were an earthquake that really split the road open, it would break this segment. The electricity would all be off because it's only energized when we're operating and driving vehicles on that roadway. And then if you can get over that broken segment, then the next section of the road would be energized. It does, yeah.
I found out
What about all of that stuff that goes on through the years? How is it with asphalt?
So the questions here about concrete and asphalt and how that impacts us. And so those are all aspects that we're going through and investigating. Now, as I mentioned, there are also multiple technologies that are going to be involved in accomplishing our goals. So the dynamic wireless charging while in motion on these roads, it's a game changer, and I'll explain why here in a moment. There are quite a few others that we're working on, and just FYI, I thought I'd show you a result from this week. So no pictures, please. It's not published. No, I'm just kidding. Just kidding. So we will get formalized announcements of this out soon with quantified results, but just for your information, we've broken a world record by a significant amount. We've now transferred over 650,000 watts, 750 kilowatts of power, and wirelessly. And this is the system sitting in our laboratory. This particular project is for, I hope this isn't distracting you. I just thought nobody wants to sit through the whole lecture. So if you're all right with it, I'm all right with it. Are we all good? All right, so this is a project that's a partnership with the partner WAVE that's here in Salt Lake City, a previous spin-out from Utah State University. They're going to commercialize and manufacture these units. It's also a partnership with Kenworth, whose truck is sitting here, and UPS, whose truck we're going to be using for a demonstration. So we are developing and demonstrating a 1 megawatt, 1 million watt wireless power charger for a semi-truck. And it's going to be demonstrated in Seattle and Portland by UPS on their truck next year. Later this year, if we can get this running, but probably next year. Anyway, so very exciting. The highest power that's been used in the commercial system to date is about 250 kilowatts. We've punched through 500 2 weeks ago. Now we're through 750. We plan to be at a megawatt very soon. Yes?
How does snow on top of the road affect it?
Question here was, how about snow? How does it affect these systems? Interestingly, much like the magnetic field itself was invisible, most other materials are also not impacting the magnetic field. So the only thing that really does are magnetic materials, like the one that I used here to shape that field. But water, snow, most dirt, depending on how much metallic component is in it, really will have very little effect on the actual field. What will affect it is the gap, the distance between the two coils. And so if you let that snow build up to 6 inches and then pack it down, and then we drive over the top of that, that could be a challenge for us to maintain the same power. But if we keep the road pretty well plowed and that gap distance consistent, that's what's really going to bring it together.
Was that 750 kilowatts transmitted or received?
Both.
100% efficiency?
In terms of 100%, okay, I see what you're asking. The efficiency of the system currently, now this is a recirculating test. So what we're doing is we're bringing the power into one side and we're transmitting it through the wireless coil and then back again. Otherwise, Rocky Mountain Power starts wondering, what are we doing? And we need some big loads to deal with it. And the efficiency of the system in that scenario is over 95%. It's probably closer to 96 or 97 when we're operating at full power. Now, there are additional components that will be added to get from the AC grid to this system and then to the battery. So the overall efficiency will be in the 94-95% range is our target. It is truly amazing. So, I mean, you're sitting here at Utah State University seeing world records happening now. Isn't that exciting? Yes?
How many cars can the wire take?
How many cars can we operate and provide power to? That's a really good question. And one of the key considerations that we're making as we develop and design these roadways. The basic concept is, again, that we have multiple modules all the way down the road. And let's say we have a 1 mile or kilometer segment that's operating. The idea is we would handle as many vehicles as we would like along that section. But we have to design the power equipment that's connecting to the utility for the maximum power of all of those vehicles. And that's an ongoing question because right now there are no vehicles compatible with this system because it doesn't exist. And so as soon as we start deploying the system, there'll be a question, how quickly will it be adopted? And how much money do we spend putting in the high power connection to the grid? Because that can always be replaced later. Anyways, my long way around saying we could theoretically handle up to bumper traffic the entire mile along that section. But in practicality, what we'll do is we'll start with, we expect maybe 5 cars, 10 cars per mile to be operating this at a time, in which case we'll size the utility connection for that. And then as it grows, we'll add higher power connection to the utility.
I guess I was under the impression that the receiver end could be connected and adapted to current cars. That's not the case, you're saying?
When I say, how many are available and how many are adopting, these could be adapted to current cars. And there are companies building retrofits for this. But we all know how retrofit goes and how many adopt and how that runs. It may or may not take off. What's really going to have this take off is having OEM equipment coming out, original equipment manufacturers, the cars that you buy at the dealer with this pre-installed. And I'll tell you in a minute, but that's going to, now if I give you too much a heads up, you'll already know the answer to one of my questions. But that's coming up. Yes? You don't really, you don't want to do that. Okay, no, it's all fine. The question is, what if you have a pacemaker and you walk over the road? So as you're coming over this road segment, and I'll just come back, oh no, I won't. As you come over these little sections over the road, as you can visualize with what the artist rendering incorporated, they're energized only precisely as the vehicle comes over them. And so you can walk over the road, you can bring a vehicle that's not electric or without the receiver. It would look like any other road. And these fancy graphics aren't nothing. It's just a road. That's all it is. And it would not impact you at all. There's a very specific safety standard that all of these systems that are being sold commercially are specifically adhering to. And it's more stringent than any other requirement for electromagnetic systems, including your cell phones and your chargers, other things. So you can stand by the road, you can walk over the road, you can lay down next to the vehicle while it's charging. However, for these dynamic charging systems, vehicles in motion, charging, I wouldn't lay very close to the road. That's going to be your biggest risk. But it's very safe and a very good question. I'll take one more and then we'll go a few more slides and I'll jump up. Yes, please. What happens when what? Yes. When you chip seal. So the simplest version of this that we're currently dealing with is straight up concrete roads. And they're long life, and there's not a lot of maintenance happening on the top of the concrete. And that's going to be one of the easiest solutions for us to start with. And we're also looking at versions of that are these precast concrete modules that you would precast in a nearby yard, and then just overnight, essentially, you could drop in and retrofit a road to be an electric road. But now if you have an asphalt overlay, or if you have a straight up asphalt road, if we come in and we do a chip seal over this, or we cut off the top couple of inches of asphalt and relay more asphalt on the top of it, Those are the fun questions. And we have a couple of civil engineers that just love that. Every time we have this discussion, they'll bring in and they'll show me the picture of their big grinder that comes over the road and grinds off the top inch of the road. And he says, "Now, how are your electronics feeling?" So we're doing detailed evaluations to understand the reliability and robustness of these systems. And these are questions that need to be resolved. We believe that this can all be handled as they have been in other industries, but that's where it's coming. All right, so with all that excitement, let me take just a quick step back in history, what got us here, and I'll see if I can very quickly, although I think everybody's here already convinced, we can probably just move on to the refreshments. There are refreshments, right? All right, so where did this come from? All right, so let's go back a bit. Let's start with the age of the horse and the buggy. Here's a highlight of London and New York. This was the era, right? So we have horses, we have transportation, we have people, all this exciting stuff. What do you think they were really concerned about when it came to transportation? What's the challenge with transportation back in the 1900 era? Please.
They needed more.
They needed more because we need more to get around. Now, what happens if you get more horses? Lots more horses. Can you imagine? Has anybody ever followed a horse before? Yes, exactly. So 2.5 million tons daily of horse manure in these cities. Over 150,000 service horses would be typical in a big city. Over 50,000 dying annually. Now, again, these aren't lasting as long as our cars do today on the roads. This was a major health hazard. What was the problem with transportation in 1900? Pollution. How did they deal with it? Well, a couple of exciting things were happening right around then. Who was I just talking about that was living in that era? Excited about AC fields? So there were things happening that were very exciting, and there were key individuals, scientists, some significant investors, that began having this vision of a whole new world, a complete transformation over where they were today. And nothing showcased it more than the Chicago World Fair in 1893, when the President of the United States pushed the button and lit up the city. And it became known as the White City as part of the Chicago World Fair. This was really, and there were multiple events before this, one of which was lighting up the Electric Avenue in London, which is what this talk was named after, which preceded this by a couple of years. So we were beginning to get this impression, but boy, at the Chicago World Fair, this is where suddenly the world realized, aha, we could be living in an entirely different era soon. Now, not everybody believed that. Some thought this was just an expensive trick or fun thing that was for the rich. Others had a vision that this would go well beyond that early stage and could ultimately transform how we live and operate. But it wasn't all about lights. What else do you think we could deal with? Cars. Kind of. Big cars. And so in that era, it was about transportation. And this was the perceived solution to deal with all of the health problems in transportation at the time. And so what happened was we began having central service, power service available in cities. And it was driven not necessarily by lighting, but by transportation, believe it or not. So we could move away from the horses and bring in public transit. That was the vision of the future. And it would be all electric. So believe it or not, who was among the first? Salt Lake City, right here in Utah, became the 5th city in the world to have central station service. And so we have a nice history in this. I give credit to James Campbell, a friend of mine from Rocky Mountain Power that helped with this first portion of the narrative. So, of course, they were beginning to immediately start thinking about, what about personal transportation? Why don't we like transit? Well, it's kind of nice to get around on our own. Here's Thomas Edison in a 1901 electric personal transportation. So 100 years from then, obviously, this vision came to fruition, right? The entire world is all electric transportation, right? Well, another big invention happened, not long after that. And that's the internal combustion engine and its use in the automobile. And then came the age of the automobile. And right about this time is the significant fall in public transit, particularly in the U.S. So the idea of a utility as a transportation company, which is really how they started, quickly changed. And they supplied power to the lights in the houses, and very quickly transportation was moving away from public transit and towards personal vehicles. So 100 years later, we're not all electric, but we do have a lot of cars, 230 million of them here in the US, more than I believe we have registered drivers. Over 3 million freight trucks, big semi-trucks operating, and some of the things that come with all this traffic. All right, so next question. What is your biggest concern about transportation? And you've got some options: air quality, cost, accessibility and reliability, travel time. This is almost like I queued you up. What do you think? What are you concerned about in transportation? You were
There's more cars, more air. Like, I don't know if but
here in Utah, it's pretty easy to see that air quality can be a serious concern. Cost is clearly a concern.
keeps going, cost keeps going.
Yeah, it changes as people come in. These are all considerations, aren't they? Now the question is, what is it going to take to bring us to higher levels of adoption? And appreciate those who have answered so far. All right, so let's continue looking into this. So what are the impacts of transportation in the U.S.? So we look at this as a nation. We're going to look at cost and we're going to look at pollution from two different angles. So cost, nationwide, it's about 16% of the average household expense, which is the second highest expense right after your house. So it is significant, believe it or not, and it's something that impacts all of us. Carbon dioxide, the greenhouse gas emissions, this is roughly proportional to the energy consumed. It's currently 29% and on the rise. It's the single largest sector for CO2 emissions in the nation. It used to be electric generation was the highest, and industrial systems weren't far behind, but there have been significant efficiency improvements in each of those. And so as the grid gets greener, it's coming down. Right now the utilities, I think, are somewhere around 23 or 24%. And it was 4 years ago or so when transportation crossed with electric generation, and it continues to rise while all of the others continue to drop. It's the last remaining holdout that is using liquid fuel predominantly for its operation and doesn't have an easy way of cleaning it up. Air pollution is what we're particularly concerned about here in Utah. As we sit in our inversion region, both here in Cache Valley and in Salt Lake City, mobile transportation, our vehicles account for roughly 50% of the pollutants in the air, at least nationwide. Okay, so these are serious concerns, but there are more concerns. I talked before about equity and access to transportation. Well, what about equity and access to clean air? Well, all of us are concerned about the pollution here as well as the cost. What about those who are in the lower income brackets? What are some of the limitations and considerations for them? Additional studies have shown for lower income levels, below $50,000 for a household, are in the 25% and even up to 50% of household income goes to transportation. Transportation is the limiting factor for many on what jobs they can pursue. They pursue jobs within their reach of transportation. Air pollution is a significant concern near high-density roadways. Some studies are showing it's as much as 90%, not just 50, but as much as 90% of the pollution if you're living in and near a high-density roadway, like an interstate or a corridor of a major city. Which populations often live in a major city near a high-density roadway? Those same ones that are limited on how far they can travel, and that's a serious consideration. How about in Utah? Do we have any population that lives near interstate highways? Well, I took a liberty of doing a conservative drawing of this. Now, some studies show that drawing to be twice as wide, and of course in Utah, it's quite different because of the inversion. So during some portions of the year, it's the entire valley that gets the same pollution. In other times of the year where we think we have better air quality, those along the interstate in these regions are also getting that 90% of the pollution from. All right, so it's a concern for sure. So the vision of Aspire. Here's what we're after: a sustainable and equitable future for transportation with widespread vehicle electrification. Meaning we want to go electric. And we see a real opportunity for this to have tremendous impact, both on our air quality, as well as the cost of transportation, as well as access to jobs. And so I'll just highlight that here. This is what we're all about. That's what we're after, and we believe it's entirely achievable, but it's going to require careful steps of the entire multiple industries to make it happen. All right, so very briefly, what could go wrong? Is there anything that could hold us up from this vision? Or in other words, is there any reason for NSF and others to be investing? I mean, it's inevitable, right? We're going to end up with clean air, low-cost transportation, and good new jobs.
So how about getting rid of the waste?
Waste, such as the batteries. How many batteries is it going to take? And I'll show you a few highlights in a moment. What are we going to do with them when they come out of the vehicle? What are the recycling options? What are the mining considerations for the batteries? Those are all serious concerns. Everything. Who said everything could go wrong?
How about the distribution? Obviously, it's going to require a lot more power.
And it's going to.
Vehicles come along.
I mean, we've seen rolling blackouts already when we've had a hot summer and challenges with, California's run into this. It's clearly there are regions in the country that are limited in capacity. So how much more is it going to take to go electric?
It's not a fun question to think about, but yeah, that one.
Who pays?
The driver's going to have to pay for the electricity. How do you track that? How do you convince the legislature that this is not going to be just billions-dollar cost?
Exactly. How do we convince who's going to pay for what? And there's another, it's a couple of interesting questions here. For example, is this straight up a tollway? We're talking to many tollways. The Central Florida Expressway in Florida is going to be running one of our pilots in the next couple of years. Tollways like they did because it kind of fits in their model. But there's a question: who's going to pay for that road? And one challenge that I might put forward is, for example, who's hurting most from the effects of transportation? Well, the poor, and it's in the cities. And they're not necessarily driving out, but they are the ones surrounded by the pollution. And it's the rest of those in the city. So it's in the city that we have the challenge. But how do we decide what cars we purchase and what determines what we can use to transport goods? It's how do you get from city to city? That's the challenge. So there's an open question. When you're driving on an interstate between two cities, should the tolling of that interstate pay for that mile by itself? Or should some of the resources of the city help pay for that, so that everybody will go electric and there will be less pollution in the city? And these are all open questions. Yes?
And can I ask, is the vision that an electric vehicle could either be charged on the road or charged at home with a
Absolutely.
is that the idea?
The question here is the vision that vehicles would have multiple options for charging, including, for example, on the road, as well as charging at home, as well as charging at work. That's absolutely the broad vision here. And only a portion of the roads would be electrified. It's these high-density roadways where the economics work and the air pollution is a significant concern. So you get into these regions, you go onto the road, it becomes a cost center for the road, and I'll talk about that in a moment. You have zero pollution at the tailpipe, in that specific region. But now when you're not operating on those roads, you also have many other options for charging, including charging at home. Yes?
So not a problem, but something that excites me about this is somebody could take a gasoline car, retrofit it with electric motor, so when you're on this electrified portion, you need to just run straight electricity. Where you get off the road, you just turn on your gas engine. Because one of the most expensive parts of electric cars is the batteries. So you don't have to have a huge battery, you have the benefits, the self reliability of the gas engine.
That's exactly right. And so the comment here was, boy, wouldn't this be a neat aspect for hybrid vehicles or for existing internal combustion that you might be able to do an add-on to make it electric? The whole concept here is that you could create zero-emission corridors. And for example, freight, that's a big opportunity. And that's something we've been seriously looking into, particularly an early adoption. Could be a first step towards this really taking off. So while we haven't electrified from Salt Lake City to San Francisco to LA and back to Salt Lake City again, where a lot of our freight runs along that little triangle, if that corridor isn't electrified yet, we could be operating with diesel, we could be operating with possibly hydrogen or other solutions between those regions, but we could take the existing diesel trucks operating in those regions, but when they get into our air district, our air corridor, they could go all electric at relatively low cost.
I'm very curious, if you go back to cars when they first started, when you first got that excitement of being able to go someplace, who was responsible for, were they facing the same kind of problems that you're facing now? And did you look, if somebody looked at what they did, how they got answers to these questions? I mean, who was it that put the roads down?
Looking back at the history, that's kind of the question here. And are we learning from our past? I'll come back to that, but absolutely. And it's something we need to look more into. Another thing we're going to hit just very briefly here is how new technologies, how new innovation are adopted. How does this typically progress over time, and how does this ultimately get to the masses? How does it get to everyone? And as we look back in history, looking at how electric homes, how did electrification get to your homes in the first place? That's another good case study we can look at. But we've also looked at the building of the highways. All right, I'll come back to each of these in just one moment. So these are all excellent points. So how do we address them? Let me just hit a couple of key points as we go along here, and then I'm sure we'll come back to many of these questions. All right, so what could go wrong? All of these things could go wrong. Now, believe it or not, I have an answer to every single one of them. And there's maybe, and then there's a percent, likelihood and confidence in every one of those answers, because that's what the research is all about. A lot of research is still needed to truly show the best path forward and to make sure that all of those items are addressed. All right, so let's just talk about a couple of these challenges. I'm going to just give a couple of personal experiences. We'll run short on time, so I'll keep these fairly brief. Charging experience. My wife likes to highlight, she thinks I've had a couple of midlife crises around electrification. I don't think that's true at all. It's just part of my career. But, one day we did wake up, and I think it was a mutual decision, but, one way or another we decided we should go all electric. And so we sold our Elantras, bought a Chevy Bolt, and loved it. Like I said, can you imagine driving down this thing and just imagining everything happening inside of that car? And it's responsive. It's like it's part of you when you drive. Anyway, you'll love it. So we drove this thing. We loved it. We enjoyed it. When we go on a long trip, our first long adventure, we plug in and electrify America. Plugged in nicely, made its little ding and noise, and our phone says we're charging, and we're all happy. We walk over to get some food, and we see the big sticker, due to COVID, big yellow highlight. No exceptions. You don't go inside, but you can do the drive-through to get food. Well, the car's charging, and we got 45 minutes to charge, so we're not going to sit in a 20-minute drive-through. So of course the car's going to stay charging. So we're walking through the drive-through. Here's my wife with one pickup truck in front of us and two pickup trucks behind us. And when we get up to this next little segment where you place your order, it doesn't pick up that we're there because, what do you weigh? So we have to walk all the way around to the counter or to where they pay, and then we gave them the order, and then we had to step aside while the cars go, and then they brought the order out. And about that time, I pull up my phone and I realize I've got about 20 messages from the charger. And 2 minutes after we walked away from it, it faulted and stopped charging. Now, 20-something minutes later, I'm looking at the messages, and it's starting to tell me, you were just charged $5 for squatting on the charger while you weren't charging. You were just charged another $5 because you're still squatting and not charging. And so we walk back across the highway, back over the charger, call them up, and they'll get the charges removed. Okay, sorry, you're having trouble. And then they say, here's what you have to do. Sometimes it takes a little bit of pressure. So are you holding the cable? You need to put a little bit of upward pressure and while you push the button to tell it to start the charge. And I don't know if these cables are big, and so you're plugged in, you're holding it up here, so we had to move the car up a little bit closer. We're holding it. Yeah, I'm holding it. And do you hear the click? Yeah, okay, now push the button. Are you still holding it? Yeah, we're still holding it. And then at one point, the individual says, are you in a hurry? So, well, I'm at a fast charger, on a highway. So, it might be faster if you move to the next one, and I'll just reboot this one, and we'll see if we can get that one going. My wife had a similar experience about a year later when we were actually selling this car to my father, who's now loving it. It was 10:30 at night, cold, winter night, and failed. Couldn't get the charging system or the billing system to work. Calls them, and the individual says, "It's not going to work tonight, but we'll give you a credit, and we hope you'll consider us in the future." Well, okay. It's 10:30 at night on a cold night, and I've got a low battery. I'm in the middle of nowhere, Utah, and this is going to work. I have no other option. And so finally, after escalating it through two managers, they managed to get it working, and she got charged. These are experiences with charging, and not all of the population is going to put up with these type of experiences. These are early adopters and innovators to take it on. So we decided to go with the Tesla and tried that for a while. And so, okay, let's see how much better this is. And it was actually a wonderful experience. We loved it. It charges 3 to 4 times faster than the Chevy Bolt did. It had a little bit longer range. Just a pleasure to drive. Again, just thinking about all that stuff happening inside while you're driving. This is a picture of, that we took while we were in Las Vegas charging, and in front of us we see an all-Tesla taxi fleet that's now been launched in Las Vegas by Captain. So that was all good. Recreation, we've been to a variety of national parks. Now again, this was a little bit of a challenge. Now we had to do a lot of studying ahead of time. Can we get there over the interstate with the Tesla? It worked out pretty well. But once we got off the interstate, this is headed up to Glacier National Park. Now there was really no option. So now we're digging through the phone apps and finding a few. Okay, there's rumor that there was somebody that let you plug in at their house, up along here. But you can get through the trip. How about reliability? Electric vehicles, this is one of the key points. There's fewer moving parts. It's a relatively simple system, except for all the fun stuff I talked about. And so it should be cheaper to maintain, easier to operate. And that's generally what we have found. But 2 weeks into the ownership, again, my wife, you're the only one with problems, isn't it? So my wife is coming out of a lunch and comes out and gets in the car, and about 20 warnings come off. And lists all these warnings. She thought it was going to explode. Tries getting out of the car, and the door doesn't open properly anymore. It does something funny and warns her this car cannot move. And so she calls Tesla. They say, no problem, we'll send out a tow truck. They said that their closest contracted tow truck company is in Salt Lake City. And so they'll send them right out. So after some negotiation, she got them to find somebody in Ogden that were willing to set out. So an hour and a half, an hour 45 minutes into the event, we're getting the Tesla up on the tow truck. Turns out there was, somebody didn't connect one of the wires on the 12-volt battery in manufacturing, and that finally caused this fault. Key point here is early stage, early technology, early innovation is going to have hiccups. It's not that reliable just yet. It takes steps to get us into higher levels of adoption. So this is what often is considered an adoption curve. And I know there are a couple of lines here, and it may not all make sense, but the yellow one, if you can see the color, going up to 100%, this is the percent market share. When do we get to 100% of cars are electric on the roads? Far left is 0%. And then that purple line is showing different segments of groups of people. The early population. So the innovators, that lower 2.5%, that's essentially where we're at today. People that are willing to pay more money, have less reliable systems, have delays in their travel. That's where we're, the early stages of a new technology. Same thing with electricity. How quickly do you think they dropped their gas lamps? When the electricity was on, 25% of the time. But eventually, again, to trust it. So right now, our research in the Aspire Center is focused all around this center section. We've been through the early innovator. We've proven the concept. These technologies work. Electric vehicles are more cost-effective. The motors are cheaper. They're smaller than an internal combustion engine. The vehicle could be cheaper and smaller. The technologies at their essence work. We've proven the wireless charging systems in their essence. They work also. But there are a few more challenges, and we listed a handful of them up there, where the majority of population just isn't going to put up with this until we get it just right. And that's what we're really investigating. What's the next step? We don't believe you can just scale what we currently have. We need new solutions. All right, so what are we up against to make all this happen? These are big markets. So first, it's the automotive market. We got to look at all of the vehicle types, light duty, small sedans, to pickup trucks, to your semi-trucks. We can't take any one small piece of this pie and call it done. Each of them are about a quarter, so we're going to have to hit all vehicle classes to really address, this is the amount of energy used by each sector, which is roughly equivalent to their, proportionally equivalent to their greenhouse gas emissions. If all those are going electric, we already talked about this, the power network is going to have a significant impact. And how does that happen? How does it roll out reliably? If all this is going to be coordinating and integrating with the transportation systems, and if, as we're proposing, some of the roadways are even going to be modified on how they're developed and operated and maintained, that's the entire transportation network. How big are these markets? They're all roughly $400 to $500 billion markets. Now, for those that don't know, that's a lot of money. All right? What money means is momentum. Big lobbies, big inertia. These are not fast-changing or moving industries typically. And now they're up against something they've never seen before. If we go from all gas to all electric, and they're roughly equal in size, that means doubling the entire power capacity of the US. But if we're going to plug in and do fast charging, that's not just doubling. That could be 5 times, 10 times. How do we deal with that? Now, not to leave them out, but if we're also talking about rethinking how we build and operate roads, that's a $300 billion business. So, we can't just publish a paper and say, wouldn't, gee whiz, this would be interesting and fun, and these industries are going to shift like that, right? That's what we're up against. So really Aspire's as much about that as it is about new technology, quite frankly. And so that's why we're involving multiple disciplines, including social scientists and engineering. All right, so some of the challenges, we've already highlighted them. We won't have time to go into a lot of detail. You know the challenges on the experience side. Batteries, just quick FYI, so that you know. What's bad for batteries is size. So long range, having to go long distances on a battery electric car, it's just not the way to go. Long term, we've got to find a better solution. Long range batteries are going to be expensive, and even as the batteries get cheaper, they're heavy, and they cause their volume. It's a major problem, and they're a big impact on the environment. Fast charging, the faster you charge the battery, the faster it decays. Bottom line, now we are looking at chemistries that'll be a little bit better for that, but they get more expensive, and still they're going to have that fundamental challenge. So if we can find solutions that don't fast charge, everything gets better. Full tank, you love running around. I mean, your mother told you, your grandmother, fill the tank, right? Don't leave the tank empty. Well, just the opposite. With an electric vehicle, if you keep the tank all the way full, that means it's fully expanded. Mechanically, it's being pushed at its limit. It's just about to burst. That's the worst position for the battery. Okay, so it degrades the fastest when it's full. So we like to keep the battery lower. The utility, the problems are high peak, high power, short amount of time, high peak power, like when you plug in your car and do a quick charge. That's bad for the utility because it has to service that, and that's expensive. The other trouble is solar power, wind power, they don't turn on like that. So it's bad for going to more renewable sources. Unpredictable, uncontrolled for the same reason. Now, many of us, put into our Google Maps, and it tells you when you're going to get there and where you're going. Fleets, they plan years ahead, if not at least weeks and days ahead. There's no reason why, when we're showing up with these vehicles, that couldn't have been predicted and couldn't have been anticipated and even programmed in, and the utility could manage that. So these are options to make this significantly cheaper and better. But to make it bad is to do status quo. So, do we keep business as usual? No. Our approach to this shouldn't be straight up business as usual. So 500-mile range semi-truck, let's just look at an example. Here's a highlight of, let's say, a current gas station turned into a major fueling station. Well, that battery for a 500-mile range semi-truck alone, not the truck itself, but the battery, would be $150,000. And you can't buy that battery today. That'd be $500,000 if you just tried going out straight up and buying it right now. But in the future, in the near future, we expect it to be somewhere in that ballpark. That's a lot. A tractor itself would typically be about half that cost or less. All right, the battery weight would be about 15,000 pounds. That's at day one. Now it'll age over time. To charge it is over 2 million watts, 2 megawatts. Your house, might have, 10,000 watts or so capacity capability. A big building would be in the megawatt range. Each truck will be like a major building in a downtown area. So cost, that's a big open question right now. But estimates are that to charge a truck fast, dealing with the troubles I just mentioned on the utility, would be somewhere in the ballpark of $1 a mile in electricity. All right, so these are challenges. If we were to convert every vehicle to electric and we had them all at 500-mile range, with the projected battery costs, we'd be about $7.8 trillion in batteries. Installed capacity. Again, that's a lot of money, believe it or not. So the question is, how long do they last? Even at 10 years, that's $780 billion a year. But they're not going to be 10 years. Some of these trucks are running 100,000 miles a year. The batteries are going to degrade. All right, so how do we do it? We're going to have to conclude here very shortly. What do you think? Well, fundamentally, we're looking at shifting things around. Now, this isn't all electric roads. It isn't entirely electric roads. But charging at home in your garage, charging at work where you typically park, charging when you're in the in and out line, charging when you're at Walmart, charging when you're pulling up to major intersections where almost everybody is going through, and charging when you're on some of the major corridors and thoroughfares on the interstates. That's what we're talking about. We're saying, let's bring the charge to the vehicle. That flips this whole thing around. Okay? Instead of saying the cars go to a gas station and those are in one central location like they are now, let's bring the charge to in and where the vehicles operate. And can we imagine a future where now, indeed, you no longer think about how, where, and when you charge. What if all of these vehicles simply kept themselves operating? And the battery sat right around 50% state of charge, half tank. And just use a little more, a little less, depending on the trips you were taking. They would last forever. You don't know there's a battery. You don't know there's charging. All right. Refreshments, I know. Hold on. We're going to end. So back to the basic concept. That was the whole pitch, essentially. We're back to the idea of an electric road as one of the key elements. This would be, again, for those major cities, high-density roadways, frequently used, multiple types of traffic. There was a question I saw rolling up there about, well, what about when it's not rush hour? We did a study around the Port of LA. It's quite interesting. If we looked at just trucks, we had these peaks at certain hours. If we looked at just passenger cars, we had peaks during the usual rush hours. If we looked at some of the other fleets and the medium-duty vehicles, we had peaks a little different. But when we put all those vehicles together, if we had one infrastructure that was supporting all of them, it pretty well leveled itself out. The total peak in the middle of the day might have still been about twice what it is at 2 in the morning, but it was much smoother because that was natural. They're naturally fitting themselves in different time slots to avoid heavy traffic. It's a shared infrastructure. All right, so the basic concept, this means it's good for the battery for the reasons I just mentioned. Now we can have smaller batteries. We're continuously providing power to the vehicle, meaning we don't have to fast charge the battery. And that means less waste. It's good for the grid because we're now providing a more controlled, continuous, predictable load. It's a moving load. The utilities never had a good predictable load, let alone a predictable, potentially controllable through some price signaling, and moving load. So that means as we have thousands and tens of thousands of vehicles circulating around a city, we can charge it in this segment, or we can let the vehicle move a mile. That's a whole nother substation. That helps levelize out the grid. These vehicles will still have some battery, and if they have, let's say, 50 miles instead of 500, 10 times cheaper vehicle. All right, you're convinced? All right, that's enough of that. So quick cost comparison. If we take a light-duty vehicle, gas might be about 16 cents a mile today. We're looking in that range, and pushing hard to see if we can get that cost down for a long-range battery and a fast-charging vehicle. But moving to this electric road concept, believe it or not, would be less than half of the price per mile. We get similar numbers when we look at the truck. And now, why is that? You're going to have to talk to me later. We'll show you some of the economics behind it. But the key component is we're taking cost out of a short-term vehicle, 10 years at best, many of them more like 5 or 8 years on the battery life. Very expensive battery to operate on vehicles. It has to be safe. It has to be high power, high energy. And instead, we're putting cost in a long life infrastructure. That's not a single vehicle that spends 90% of its time parked. But it's a roadway that spends at least a quarter of its time, if not half of its time, supporting vehicles throughout the day. And it's sharing that infrastructure to all vehicle types. And much of the cost of that would be covered by the freight, the heavy duty that need the most energy. That's why this cost was so low for the sedans. All right, that's the basic concept of the electric road. Shifting cost from single-use vehicles to shared use in long-term infrastructure, 20 to 40 life infrastructure. All right, so that's the basic pitch. I won't hold you up on all of these points. Last question, which I just skipped, is when are you going to be driving on that electric road?
When I can buy the ID Buzz W.
And you're going to buy that, and it's going to be the small battery version. It's going to be cheaper than the current internal combustion. So we envision there could be a massive electric. We could have $12,000 electric vehicles that could go from San Francisco to New York nonstop. Wouldn't that be exciting? All right. It is happening today, believe it or not. These systems are now being offered by Hyundai commercially. You can buy a vehicle, you can order it with the system already installed. Every vehicle OEM we're working with, and that's essentially all of the major ones, have systems where they're looking at releasing charging systems. We have commercial charging systems out there, such as this 250 kilowatt system by Wave operating today in California. And believe it or not, we have dynamic wireless charging systems in operation today in pilots, currently in Europe, and now just recently announced happening in Michigan. Our system is going to be happening here in Utah. Multiple are coming up very soon. We're doing research around these components, all kinds of exciting things in and around that. We have demonstrations at Utah State University at our facility. I'm going to invite you out here shortly to come out and see them. That includes operations with all of those vehicle types and with our international partners. And we have a significant amount of funding, over $45 million committed at pilot funding for us to take these technologies and go vet them out and answer some of these questions you just asked. When will this really work, and when won't it? So we're doing it here in Utah, south of Salt Lake, in and around the inland port. We're also working on a project on an electric train together with Stadler, where they're developing the train and we're showing what the implications would be for Utah on that train. We have another one in Florida, just near Disneyland, and then our partners Purdue are working with Indiana and INDOT. Believe it or not, this is actually happening today. These are all going to be in operation over the next 2 to 3 years. We have a roadmap that would see us over the next 20 years fully deploying these systems and getting them out across not only the corridors in our cities, but also now reaching between major cities and really advancing electrification. All right, that's where we're headed. The Aspire Research Center is all about combining these components across disciplines, across industries. We'd love to get you involved. I already told you how many universities. We have over 60 companies involved. It's all about how we're doing it, not just what we're doing. All kinds of exciting opportunities to engage with students from a variety of areas. And finally, oh, I got to say, we're building a new building. Love to have you come see that too. That won't be here for about another year. This will sit on top of where we're at currently. Look, we've been here before. We know what it takes to have major infrastructure developments as a nation. Wouldn't it have been exciting 100 years ago to see Chicago light up and start just be part of this idea of what if the entire nation were to change based on this technology? That's where we're at today. Come join us. We're doing an open house May 19th. We'd love to have you come out, touch, feel, ride the bus. A lucky few will drive the ride in the truck. We'll do this. Custom tours, if any of you know schools that would like to partner with us, we're happy to work closely with you. We're developing curriculum specifically for high schools and middle schools. We'd love to work with your teachers. And finally, come become an engineer or work with an engineer from any one of our partner disciplines. We have scholarships available. We can get you involved even as a high school student in summer internships. I know we've run over. This has been fun for me. I know we've got things to get to outside. I wanted to ask you the question. I assume now the answer is everybody wants to be an engineer. Thanks again for your time.
Thank you very much. We used a lot of our time for questions already, so I think we'll keep the question and answer a little bit short. In fact, let me start by taking a couple from our online viewers, since they had some pretty good questions here. One was really to ask about more specifically how you plan on implementing this program into existing roads.
The plan to incorporate these systems into existing roads, we're looking at both, as I mentioned, concrete roads as well as asphalt roads. For asphalt, though, we can show an example of how one of our partners, Electrion, is implementing this. They take the existing asphalt road and they cut just a center section, some inches deep in that road, and then they just lay their system down in, and then they just pave right back over it. We're also working on solutions that are based on precast concrete modules, where again, we would just cut a segment out of the existing road, place in the precast segment, and then fill in over those gaps. Then you could put another inch or 2 or 3 of asphalt as appropriate. So we're looking at those options. Now, the cheapest solution is to work within the maintenance schedule of the roads. Ideally, we're not going to take a road that was just finished last year and next year go add this system. But over half of the roads in the U.S. today need upgrading and need effort. So the timing really is good now to fit this right into the maintenance schedule of the next 20 years. That would be sufficient to really bring this about all the roads.
One more online question I'll raise, and then maybe we'll take 1 or 2 from the audience. This one, I'm not sure I understand it exactly, but I think it's basically a question asking, what's the best way to find out more about this project? Where's the best place to read about it?
Now you're striking a chord. Websites are the bane. It kills me that this isn't all on our website, but it will be soon. Right now, the best place, we do have good information on our website, and that also includes contact information for many of the leaders within our program. So right now, contact the Aspire team. Reach out to us. We'll lead you to key publications in the space, and we'd be happy to host you at our site.
Great. I have a microphone here if somebody in the audience wants to ask a question. Yeah, you can just talk into this, speak into this, you see? That way everybody can hear you.
What happens if the battery starts exploding?
If the batteries explode, you get out, quick. But again, the interesting thing is they typically don't explode. What batteries can do is they can overheat. And as they overheat, they could go into what we call a thermal runaway. Now that again is something that they've specifically designed. That's why the batteries are so expensive. Now, only certain batteries are in the cars. It's a different battery than you have like in your remote controlled airplane or car, or those are much cheaper and they explode, they burn more easily. All right, so the batteries in the vehicle are exceptionally safe. And if they ever do get to a point where they overheat, and if they were to go into this thermal runaway, it would be a more gradual event as it gets started. When you notice this, you stop and you get out. And don't get back in. I would just call for another ride.
Catch.
Hey, that's cool.
We just passed a 1.9 trillion infrastructure bill. How is this going to tie into that?
we are all still trying to figure that out. But the infrastructure bill will certainly have an impact. And so it's going to have an impact on our ability to advance the transmission hand capability, our generation capability, some to extent the distribution capability on the utility. It's going to impact some of the related infrastructure that we're building for EV charging. So it's going to help advance this field for sure. And we're involved to sort all that out. We're still waiting for the government to release some of those details.
Time for one more question if you have one. Yes? Here, I'm going to throw this to you. Can you catch it? Ready?
Was the original video a simulation, or is it operating right now?
Say that one more time, the what?
Was the original video a simulation, or is it active right now?
Really good question. So the video that we just showed, the vehicle is an all-electric bus, and it does operate over wireless chargers now. The version in the video that indicated multiple chargers stacked all the way around the track, that is a simulation. And so that's what we're actually implementing this year. And in fact, through this summer, we're implementing 3 different versions of the technology, including the version from our partner Electrion, who's deploying it next year in Michigan. So they're going to vet and evaluate the technology here in Utah first. And you're all invited to come out and see it first here. Then it's going to be deployed once everybody's comfortable with it in Michigan. So that's to come. Can't pull anything over your eyes. Appreciate the question.
There's some questions there if you want to
Yeah,
talk to
we've
one.
got a number of good ones. The cost of roads will increase, and the cost of roads will also increase. Will it be cheaper than gas?
One of them supposed to be cost of electricity.
Yes. So here's a good question. Now, it could go any one of these directions, and that's why we're doing careful research into how to do this right. The numbers that I just put up were based on our models of if we do this right, which means it's not just a brute force, throw it in, and then see what happens. But if we do this with care, we implement the electric roads in a way that's coordinated with the growth and loading on the electric utility. And we do this in a way so that we can help use the vehicles as a resource to balance the electric utility. That means this all has to be part of the overall planning of both the transportation and the electric utility. If we do all that right, we actually believe now the vehicles will help levelize the loading on the utility, because we'll now have these roadways that are well predicted, average loading the utility can predict. By doing so, what this actually does for the utility is it makes the entire distribution system more cost effective, which means electricity rates could actually go down. You know, it costs 2 to 3 cents for generation, for example, of solar and many other sources per kilowatt hour. But none of us pay that rate because it costs a lot of money to transmit that electricity and have substations, et cetera. We actually believe that if we do this right, we could use the additional loading of the electric vehicles and the predictable loading of the electric vehicles to bring down costs, not just of operating electric vehicles, but even your house and loads at your home could become cheaper by doing this right. Roads, the cost per mile of building the road will definitely be more expensive because we're incorporating equipment. But as I just mentioned, now that road is becoming a revenue source instead of being just sorry to the civil engineers, not just a road. But in addition to being this amazing, facility to drive on, it now also is a resource for delivering energy. So that cost is recouped with the price per mile that I just highlighted.
It's a good place to stop maybe. So I'd ask you all to thank Professor Zane again, please.